and valence electrons in a particle. Now the particle could be an atom, it could be an ion, or it could be a molecule. It also identifies any formal charges. So that's great. So a Lewis structure then has to give me the number and arrangement of all the atoms in a species. It has to give me the number and arrangement of all of the valence electrons in a species. It also has to tell me which atoms, if any, are charged and what is their charge. Right? That's a heavy mandate for a Lewis structure. Okay, so let's do some examples. Let's say I asked you for the Lewis structure of cyanide. Well, let's start with something easy. Well, it's fine. Cyanide. Now, as a rule of thumb, I will rarely ask you to draw the Lewis structure for anything. What I will ask you instead is to build the Lewis structure. And the reason that's important is I need you to be able to construct the Lewis structure for a species based on first principles, even if it's something you've never seen before. Now, all of you probably know that from your Gen Chem 1, that the Lewis structure for cyanide looks like that. And if I ask you to draw that, that's just a question of recall. And you need to be able to build it because a lot of the species you will see in organic and biochem and inorganic chemistry are going to be unfamiliar. You need to have a protocol for how you come up with the Lewis structure. So here's what we're going to do. First of all, in a case like this, we want the number and arrangement of all the atoms. Well, it's Cn. There's only one way to do that. It's C attached to N. Whoop-de-doo. So that is my arrangement of the atoms. That's the number and arrangement of all the atoms. First mandate finished. But what I want is the number and arrangement of the valence electrons. So let's catalog the number of valence electrons. So, for carbon, so the number of valence electrons is going to be equal to 1 times 4. Carbon is the element number. Carbon is in group number 4, so it's got 4 valence electrons. Plus 1 times 5. Nitrogen is in group 5, so it has 5 valence electrons. So I'm just counting, doing an inventory. And there's a 1 minus charge, so plus 1 for the negative charge. So to get the number of valence electrons, I multiply the number of atoms by the group number. Because that's how much they're bringing to the table. I have 1 carbon that brings 4 valence electrons, 1 nitrogen brings 5 valence electrons, and I've added an additional electron. So that gives me 10 valence electrons. Okay, good. Of those 10, I've consumed 2 in my structure. There are 2 electrons here already. Okay? So, what I now have is 10 minus 2, that is 8. I have 8 valence electrons to play with. At this point, my rule is I want to make sure the atoms have noble gas configurations. So what if I decided to take my 8 electrons and say 2, 4, 6, I'll have to stop here because the carbon already now has an octet. It's got 2, 4, 6, and I share those 2 electrons. That's an octet. And I'll have 2 now on the nitrogen. So that gives me the number and arrangement of all the atoms, the number 2, 4, 6, 8, 10, and an arrangement of all the valence electrons. What it does not give me is the formal charge. So let's go ahead and see if there are any formal charges. So I'm going to slide this one over here because we'll be doing a fair amount of manipulation. So I'll have C, N, 1, 2, 1, 2, 1, 2, 1, 2. So what about formal charges? How do we work that out? Well, and I know there's something funny because I need to have a negative charge. So how do we figure that out? Well, what we're going to do is ask ourselves 2 questions. How many electrons belong to each atom? And then I'm going to ask, how many should it have? And I'll ask a follow-up question. If it has more electrons than it should have, it'll be negative by the number of electrons in excess. If it has fewer electrons than it should have, it'll be positive by the number of electrons it's missing. Carbon is a group 4 element. It should own 4 electrons. How many does it have? 2, 4, 6 are lone pairs. They belong to carbon only. And there's also 1 electron in that bond that belongs to carbon, right? When atoms bond, you imagine 1 electron, each atom brings in 1 electron. So 1 of the electrons in this bond belongs to carbon. So this carbon has 2, 4, 6, and 1 in here. That's 7 electrons that it owns. But it's a group 4 element. It should own 4. It's got 3 electrons too many. That's a 3 minus charge. What about the N? Well, the N owns 1, 2 in the lone pair. That's entirely for the N. But it also has a share. It also owns 1 of those electrons in this bond that it's sharing with the carbon. So really, it's got 1, 2, 3 that belong to it. But it's a group 5 element. It should have 5 valence electrons. It should own 5. This one only owns 3. So it's missing 2, which means there's a 2 plus charge on that nitrogen. This actually makes sense. Because if I sum the charges, I get the 1 minus. Okay? So this is a Lewis structure because it does what Lewis structure should do. It gives me the number and arrangement of the atoms. 1C, 1N connected to each other. It gives me the number and arrangement of all the valence electrons. All 10 of them. Whether they're lone pairs or they're bond pairs. Doesn't matter. I know where all 10 are. And it also gives me the formal charges. That's a Lewis structure. Now, I can now assess the stability of that Lewis structure by looking at it. Is that a good Lewis structure? It's a good one because it's a correct one. Is it the most stable structure of cyanide? The answer is no. And the question is, why not? What's wrong with it? And the answer is a bunch of stuff. 1, the reason elements bond is to acquire a noble gas configuration. This carbon is perfectly chemically happy. It has an octet. 2, 4, 6 that it owns and is sharing 2. That's an octet. The carbon got what it came for. The nitrogen doesn't have an octet. It's got a quartet. It owns 2, it's sharing 2, that's a quartet. So the nitrogen didn't get what it came for. That's not a happy chemical. So I'm trying now to determine how stable we are, and the first thing I look for is number of atoms with noble gas configuration. The second thing I'm going to look for is the number of bonds. The number of bonds. Because I know bonds stabilize. So the more bonds I have, the more stable I am. And we'll explore that in some more detail. There's only one bond here, and carbon is capable of forming 4 bonds. N is capable of forming 3 bonds. And yet between them there's only 1 bond. So that can't be good, right? Because they can do better. And more bonds I have, the more stable I am. And the third thing is the degree of charge separation. So what does that mean? If I have a particle, xy, and I tell you xy has a charge of, let's say, +1. Well, that could happen in a couple of ways, right? Y could be plus, that's one option, or x could be plus, that's another option. Another option is y could be 3 plus, and x could be 2 minus. X could be 10 minus, and y could be 11 plus. Now all of these are xy plus 1. But here, I've separated out the charge, so one particle is charged. And the charge is low, it's a 1 plus. But I could tease out the charge more, so that both atoms are charged. One is 2 minus and one is 3 plus. That's greater separation of the charge. This is even greater still. If you had to fathom a guess which of these 3 is best, the answer is that one. Because fewer particles are charged. Nobody likes to be charged. Nobody likes to be charged. And if I must be charged, I want the charge to be as low as possible. Now, I will accept being charged if it gives me a noble gas configuration. That's what lithium plus did. That's what lithium did to become lithium plus. That's what fluorine did to become fluorine minus, because it acquired a noble gas configuration. And let me just make a point. So if I had lithium plus in a vacuum, that's a terrible scenario. Even though it's chemically stable, it's physically unstable. So what happens? The fluorides around it form bonds with it, and the bonds stabilize it. Okay? So in a species like this, I can say this is not particularly stable because the N doesn't have an octet. That's rule 1. The number of bonds is low, and the charge separation is massive. Another way we can look at the charge separation is to ignore the sign of the charge and just look at the magnitude of the charges. So in this case, that's a magnitude of 1. Right? Ignoring the sign, this is the magnitude of 5. Ignoring the sign, that's 21. So there's increasing charge separation in this way, decreasing stability. Okay. Can I fix this structure? The answer is absolutely. And I'll do this quickly. Yeah. So, what do I need to do? Well, the N needs to get a noble gas configuration. N needs electrons. Well, where would electrons come from? And the answer is from the electron-rich species. The N is electron poor. Does not have an octet, poor. It's got a positive charge, poor in electrons. The carbon is negatively charged, it's electron-rich. Electrons flow from electron-rich to electron-poor. So I'm going to take a pair of these electrons and move them between C and N. Okay? That's going to give me a structure that now looks like this. What did I do? I took a lone pair of electrons and I made it a bond pair. I left the 2 lone pairs alone and I left that lone pair alone. All 10 electrons are still here. 2, 4, 6, 8, 10. What about my charges? Well, how many electrons does the N own? 1, 2, that belong to it alone. 1 in that bond, that's 3. 1 in that bond, that's 4. It's a group 5 element. It's still missing 1 electron, hence a positive charge. What about the carbon? 1, 2, 3, 4. 1 in this bond, 5. 1 in that bond, 6. It's a group 4 element. It's got 2 too many, hence a 2 minus charge. And again, when I sum these, the overall charge is 1 minus, so I know I'm on track. Am I done? No. Why not? The nitrogen does not have an octet. No, it's closer. It's got a sextet, 2, 4, 6, but it doesn't have an octet. Can I fix it? Absolutely. I'm going to take 2 of these electrons and dump them here again. Electrons flow from electron rich to electron poor. And I'm going to end up with this structure. What's the formal charge at the end? Well, it's got 1, 2, 1 in here 3, 1 in here 4, 1 in here 5. It's a group 5 element. So it has neither an excess, so it's not negative, not a deficiency, so it's not positive, so it's neutral. No charge at the end. What about the carbon? It's got 1 in here, 1 in here, that's 2, 1 in here, that's 3, 4, 5. It's got 1 electron too many, this is a group 4 element, hence a negative charge. Okay? Now, everybody has an octet. Now, there are a couple points I want to make. 1. It doesn't matter where I started from at the beginning. So whether I had put 2, 4, 6, 8, or 2, 4, 6, and then 2 here. It doesn't matter where I started. I would have ended up at the same place. And I'm going to invite you as a practice exercise to start off at different places here. The other point is that there's a systematic way of doing it. Once we've got a Lewis structure to start, we want to look for how electrons are going to flow. Electron rich, electron poor. Let's examine this analysis in one other way. So I know that there is a 2 plus charge in this end and a 3 minus charge in this carbon. When I move those electrons and I make this structure, I could go back and count how many I have, how many I should have, and see what the difference is to get the charge. I could. That's what I did here. 1, 2, 3, 4. I'm in group 5. I'm missing 1 plus charge. 1, 2, 3, 4, 5, 6. I'm in group 4. I've got 2 too many, 2 minus charge. I could do that. But I could say, look, what this action does is that I end up sharing an electron pair, which means you get 1, I get 1. So it means this carbon is in essence then giving away an electron to the nitrogen. Well, for heaven's sake, if I'm 2 plus and I gain an electron, I'm going to be 1 plus. If I'm 3 minus and I give away an electron, I'll be 2 minus. I did it again. I took a lone pair, which belonged to carbon only, and I'm sharing it with the nitrogen. 1 is yours, 1 is mine. So I am 2 minus, and I am giving away an electron. I am now 1 minus. I am 1 plus, and I am gaining an electron. I am now 0. So I could have figured out the charges. I can figure out the charges either by counting how many do I have, how many do I own, how many should I have, what's the difference, what's the charge. Or I can say, I can reason it the other way and say, look, I know I'm positive, I'm gaining an electron, I'm not neutral. The last one is, if I were to ask you to rank these, let's call them 1, 2, and 3, in terms of increasing stability, how would I rank them? The answer is, well, let's see. Do I just have a gut feeling about it? Do I just, do I form an opinion? And the answer is no. This is science. Right? There are rules and there are parameters by which we gauge stability. And what are they? Number of atoms with noble gas configurations. Number of bonds. Degree of charge separation. In other words, the more atoms with noble gas configurations, the more satisfied everybody is, the more stable we are. The more bonds I have, the more I stabilize. Bonding stabilizes. The lower the degree of charge separation, the fewer atoms that are charged, and the lower that charge, the more stable we are. Because nobody likes to be charged, positive or negative. So I have three parameters by which to gauge stability. So of the three, here, everybody has a noble gas configuration. I've got the most bonds and the least charge separation. So particle 3 is the most stable. Followed by 2, where I've got fewer bonds, the carbons in an octet, the N is a little bit close, and the charge separation is a modulus of 3. Right? If I ignore the sign, it's 2 and 1. And of course, this one is the least stable because the N is furthest from the octet. I've only got one bond, and there's a massive charge separation. Okay, so we'll stop there and pick it up in the next lecture.